So alkenes are unsaturated hydrocarbons that contain at least one double bond, carbon to carbon double bond, and general formula is CnH2n. The physical properties of alkenes are similar to alkanes, okay? Because there is just a difference of two hydrogens, but the chemical properties are quite different, okay? And apart from this, alkenes shows both structural and stereoisomerism. Okay, structure we already know that just have to change the structure. You have to change the carbon double bond, and the structure will be changed. And stereoisomerism is due to the cis trans carbon to carbon double bond carbon rotation. Okay, restricted carbon double bond rotation. So that is the stereoisomerism is due to that. Clear? And if we do some namings, okay, I'll just be very quick with that. Like if I ask you to name this compound, okay, what we do in the structure formula, what I told you that we always have to show the double bond, okay. CH will make it 2. So this will be propene. So and if I just make one more, mm, like if we add a methyl group here and we just double bond it with the other one, so it will be 2 methyl propene. Okay, so it's just that. Okay, naming is usually easy of alkenes, not that difficult. And in the cis trans terms, we have already discussed that. Okay, it's how we make cis and cis and trans isomers. Coming on to the reactivity and the reaction of alkenes. Again, we will first discuss how much reactive alkenes are and why they are reactive. So alkenes are reactive due to the carbon double bond, okay, that is present. So the double bond contains, I'll just write point by point, okay, alkenes contain carbon double bond, okay. Now this carbon double bond has one pi bond. If you look closely, okay, there's one sigma bond and one is the pi bond. So pi bond has high electron density. Okay, pi bond is the area where there are the dense. Okay, there are so many electrons that are gathered there. So that is a high density area. So that is open to attack. Okay, whenever you have a high electron density area, that area is open to be attacked by someone who does not have electrons. Okay, someone who is positively charged, someone who needs electrons, that will attack the high electron density area. So pi bond has high electron density, which is open for attack by an electrophile. So electrophile are the ones that have positive charge, that have no electrons, that have deficiency of electrons, and nucleophiles are the ones that have a lone pair or two lone pair of electrons or more. Okay, so they are electron sufficient, and the electrophiles are electron deficient. Okay, so alkenes mainly go under electrophilic addition. This is our second mechanism that we will study now. So I already told you that the name of mechanism shows us that what the reaction is doing and who the what species are you the which species is reacting in the overall mechanism. So electrophile is going to be added, okay, in the alkene. So let's just look now into the electrophilic addition. So first of all, what happens that if I place I'll just make a rough diagram, or I'll show you a diagram. Yeah, I have one diagram. Okay, this is just a conceptual process. Then we'll make the like how we're going to answer the question in the paper. We're going to look that after this. Okay, what is happening that you bring. Okay, this is your alkene. Okay, now you know alkene has a double bond. The pi bond is being shown here. Okay, by a lobe type structure that it shows you the electron dense area. So when you bring a molecule that is electron deficient, okay, that is already, for example, you are bringing to HCl. Okay, so HCl is a polar molecule. Why? Because they both have different electronegativity. Polarity arises from electronegativity difference. Okay, chlorine has different electronegativity, hydrogen has different. So what happens? The induce partial charges on each other. Okay, what does that mean? That if the electrons were bonded in the middle, now they are more attracted towards chlorine, because chlorine has higher electronegativity value. Electronegativity means power of an atom, of an element, to attract the electrons towards itself. So chlorine is attracting the electrons more comparatively to the hydrogen. Okay, so now the polarities, the dipoles, or we could say the partial charges are now induced in the molecule, and it is a polar molecule. Okay, now what happens when you bring this molecule closer to the pi bond area, to the carbon-carbon double bond, obviously. So what happens? The positive partial charged element, that okay, that one, like X is in this case, is attracted more because it has a partial positive, so it will be attracted to electrons. Electrons are negative, right? So that area is of, you can think it of it as a negative area. So this positive element will be attracted more, and when you are getting closer to the electron density area, the electrons are moving further back down. Why? Because electron to electron repel each other. Okay, so these are electrons are getting further away and towards the Y element that was already negatively charged. Okay, that will also not attract because negative repel. So what happens after that? I think we should just keep this diagram here. These are like a step-by-step diagram that what is actually happening. This is your step 1. This is your then step 2. In step 2, let me paste the diagram. Okay, now what is happening? The X atom eventually got what bonded, got that much attracted that it uh, broken down the the bond with the Y atom and got bonded to the carbon. Okay, on the that was of the to carbon double bond. Okay, and now what happens? This carbon has now three bonded, so it's one remaining, so it needs to now bond with someone. Okay, because the this X element was not coming with any electrons. So what happened? So both electrons were bonded in this, okay, with X. So this carbon was left with one electron deficient. So now this Y ion hai, okay, that Y ion will be coming towards the carbocation. Now we call it the carbocation because this carbon has a cation sign. So now this will be attracted and it will form a dative covalent bond. Okay, we usually don't show it, but it is a dative covalent bond because both electrons are being provided for bonding by the Y element. Okay, so now in the third step, this will be bonded. I'll just mark it. This will be bonded to the next carbocation. Okay, and now that you have overcome, you have removed the double bond, and now these two elements you have added in the alkene, and now it is made, it could either be alkane, it could either be halogen alkane, it could either be alcohol. Okay, you never know what we'll see in the further reactions. So is it clear? Okay, now how you're going to actually uh, you just have to make the arrows, dipoles. So for that we'll do a mechanism like CH2 double bonded to CH2, and if you have brought we'll say HBr, I'll just make X and Y. So first you have to write the dipoles, the partial charges. Okay, then you have to make an arrow like this. One arrow will be like this. Okay, and the other arrow will be like this from the middle to this, like what is going on, that X is trying to break the bond with the Y and needs to get attracted, needs to get bonded with the carbon atom. So in the next step what happens, that this becomes CH2, the H got attracted here, got bonded here, and this became plus carbocation. And now the Y was left with a lone pair, and it has a negative charge here. Now we're going to draw an arrow towards the carbocation like this. And now you just know what happens, that both are bonded. Okay, no, we kept X here, not Y. Okay, X was here, so it will be CH2X, CH2Y. Acha, okay, no, now note the arrows that we have. Okay, we have three arrows. Okay, we have one lone pair in the whole mechanism, and we have two partial charges in the whole mechanism. Because as we as you doing more mechanisms, you will be getting confused. Okay, so you should remember that in electrophilic addition, and you should have to be practicing it a lot, okay, because in the next mechanism you will getting quite confused with the previous ones. Okay, now how do we decide where to send X could have been bonded here as well, X could have been bonded here as well. How do we decide that? Okay, for that we have a rule. We call it Markovnikov's Markovnikov's rule. Markovnikov's rule says that the addition of hydrogen, okay, every if you have addition of H and X, okay, H is always there if you have hydrogen and you have another element on the other side, okay. In alkene, the hydrogen, because every time hydrogen will be getting bonded first. So where do you have to bond hydrogen? The hydrogen bond itself to the carbon with already greater number of hydrogens. That carbon that already had more hydrogens, okay, you are just comparing two carbons, right? Carbon number 1 and carbon number 2 that had double bond in between them. So the one carbon that had more hydrogens with it, that carbon will be getting that hydrogen attached to itself. So for example, if I have one, I'll just draw an example: CH3, CH, CH2. Okay, and now you're trying to add HCl with it. So you are getting two products here. Okay, both products will be formed, but one product is the major product, one product we call it as a minor product. Okay, major product is the one that is produced in the greater quantity, and minor is the one that is a vice versa. So in our example, CH3, now you have to compare this carbon and this carbon, right? Which carbon already has more hydrogen? That is a third carbon. So CH, you will have Cl here bonded, and CH3, the hydrogen will be bonded on the next carbon, the last carbon. So this will be your major product. And the minor product, that is the opposite of Markovnikov rule. If you are not following Markovnikov rule, so it will become CH2, hydrogen will be attached here, and CH2Cl will be your minor product. Okay, clear? So this one is 2-chloropropane. Okay, you should also do the naming. And this is one chloro, or you just have to write it one chloropropane. Okay, that is also fine. Okay, so why is it necessary to do this? Okay, why do we have to follow Markovnikov rule? What is the concept behind it? We'll study that here. So whenever you have a carbon chain, suppose I'm getting an alkene. Okay, so in the mechanism we saw that this state was formed, okay, in which we had one carbocation and one carbon was bonded. This state we call it as an intermediate state. Okay, because it is in the middle of the mechanism. So you can call it as the carbocation is the intermediate, is formed as an intermediate, okay, during this reaction at this stage. So what happens? You have three types of carbocations. Okay, three types of carbocations we can classify. What are the three types? First type is uh, primary, secondary, tertiary. The primary carbocations are the one which has already two hydrogens attached to him. You have a carbon chain. I am denoting the carbon chain with R. Okay, you have a carbon chain on the back of that. Then you have this carbocation plus, and you have two hydrogens attached to it. Okay, now the three bonds are already done here. You just have to add one more. The electrophile will be added here, and then the carbon is completed, the valency. But this intermediate, this is the primary carbocation. Then, if you have R here, the carbon chain on this side, then H here plus, and now you don't have one H, you have another carbon chain on this side too. Okay, so what you have done, you have made the middle carbocation. So this is the secondary, which has only one hydrogen with it. This is what we call a secondary carbocation. You just have to remember the number of hydrogens with it. Okay, how many hydrogens are there with the carbon? You just have to remember with that. Okay, and the third will be the one which do not have any hydrogen with it, which means it has all the carbon chains attached to it on three sides. These are three types of carbocations. Clear? This concept will be very important. You will be studying this again in the halogen alkanes. You will be studying this again in the alcohols, the primary alcohol, secondary alcohol, tertiary alcohol. Again, you have primary halogen alkanes, secondary halogen alkanes. Same concept will be applied. Okay, you just have to see how many carbons, how many hydrogens are attached to that carbon. Now, the carbon chain, the R chain that we are basically telling, the carbon chain has electron pushing effect. Okay, what it does, it tries to push electrons towards someone needs the electrons. Okay, they are electron donating group. Okay, the alkyls, I'm telling the carbon chain, the alkyls. Okay, basically the alkyls will be attached on the back of the side. The alkyl chain, the carbon chains are electron donating group. They have the quality that they donate the push electrons towards someone that needs it. Okay, so in primary I can see there is only one group of carbons that are pushing the electrons towards the carbocation. In this we have two groups that are trying to donate the donating effect. Okay, they are actually not donating the carbon to electrons to the carbocation. They are trying to make a effect that we are donating. This just a effect. They are actually not donating it. Okay, they are just moving their electrons toward that carbocation so that it feels safe, it feels stable. Okay, because it needs to overcome this positive charge to become stable. So try to make it feel stable. They are trying to push their electrons toward that carbon. Okay, and in the tertiary one you have three groups that are trying to induce the donating effect on the carbohydrate. So, what do you think? Which carbocation will feel the most stable? Hmm. The tertiary carbon, the tertiary carbocation, it will feel the most stable, okay, because three electron donating the alkyl chains are inducing the donating effect on the tertiary carbocation. So I'll just write it. Electron donating effect. They tend to push electrons towards carbon atom, which carries a positive charge. So, if we take a realistic example,